To present a work about analytical query on the linked open data cloud. This is a joint work with Fabian Souchanek from Telecom Paris. First, I will explain what we mean by analytical query, and after I will explain some limitations about public Sparkle endpoints due to fair use policies, and I will present how we reformulate our problem in this context by using an anytime approach. And finally, I will present an algorithm and some experiments. So we are in the context of the linked open data cloud, and we are interested in knowledge-based profiling thanks to analytical queries. For instance, analytical query is more or less a group by query. For instance, we want to know the main properties and the main classes which are used on the load. Interestingly, in our framework, we can use advanced queries based on subqueries and multiple aggregates. For instance, here we compute the number of subjects for a given number of objects and a given property. What it means, for instance, here on this toy example, we have 2 triple stores, and for each property and each cardinality, we try to find the number of subjects that have exactly, for instance, here, 1 object for the property gender. So here there are 9 subjects in that case. Why it is interesting? Because thanks to these statistics, we can compute high-level indicators, for instance, maximum cardinality constraints and many other ones. I will illustrate that at the end of the presentation with a use case. So this kind of queries are really useful, but unfortunately they are very hard to compute from Sparkle endpoints. For instance, if I execute this query on Wikidata or on DBpedia, I don't obtain an answer. I have, in the first case, a timeout, and in the second case, I obtain an incomplete answer. Because there is a limitation, a time limitation for each query. So what could be a solution? We have a different approach in the literature. The first approach is federated query system for querying multiple endpoints. This is a nice approach, but unfortunately, this approach is well designed for a dozen of endpoints. And in our case, we have 100 endpoints, for instance. And to the best of our knowledge, this approach does not cope with the problem of fair use policy. So the main approach in the literature is to centralize all the data in the local server, and then there is a processing which is done with distributed architecture for like Adobe or Spark, for instance. So this is an approach which is costly in communication and in execution time. There are also other kind of querying system, for instance, fragment, but in the case of analytical queries, this is more or less the same thing that data centralization, because all tuples are involved in the result of the query. So we decided in this work to adopt another approach. We are going to propose an anytime approach that gives successive approximate answers that converge to the exact answer. So basically, the main idea is to have a sample of small analytical queries which are launched on each public Sparkle endpoint. And after, we aggregate all these small results for approximating the final answer. Of course, each subquery has to be compliant with fair use policies. And we want that the approximate answer converges to the exact one. Unfortunately, there are two main challenges to tackle. The first one is how to partition an analytical query into smaller queries. And the second challenge is how to implement a federated sampling system on the load. So I come back to the initial example. I often denote the query by alpha card. And the first observation is that I can split this query for each triple store. Here, for instance, there are 6 subjects which has 1 gender in the first triple store and 3 in the second triple store. And I can sum up these 2 queries in one by using a simple sum. But as I said before, we need to partition even one triple store because in general the analytical query is too heavy for the fair use policy. So the first idea is to put a restriction on each object for partitioning the data. Unfortunately, if we do that, we obtain that we count 3 times that Gaius has 1 child instead of 1 time he has 3 children, because the 3 triples are not in the same part. Another way could be to use a restriction on the property, but in that case, it's right, the 3 triples of Gaius are in the same part. Unfortunately, in general, this kind of query is too large and non-compliant with fair use policy. And the good way here is to partition according to the subject, because we can observe that the 3 triples of Gaius are in the same subquery. But this is a very small query, so we can easily launch it on a triple store. Okay, so imagine that we have now our set of subqueries. We know which are these subqueries. We have to sample them on the load for obtaining a good approximation. We are going to use a 2-step random procedure that basically consists in 2 steps. The first one is to select 1 triple store with a probability proportional to the number of subjects. So in this example, the first triple store has twice more chance to be drawn. And in a second step, we are going to uniformly pick a subquery in the selected triple store. The main difficult part in the first step is to compute the number of subjects and the weight of each triple store. So a naive way could be to count the distinct number of subjects in that case, but this query is probably non-compliant with fair use policy. We could also use a unique relation like a gender, but we know that this relation is probably not existing in a real world. So we decide to use an approximate weight with the third query here. We just count the number of triples. We obtain 11 instead of 6. So we overestimate this weight, so we have to correct it later. For drawing uniformly a subquery, we are just going to use a limit clause and an offset clause. But in the case of the last query, we have 4 options for picking Gaius. So we have to reweight this query by 1 out of 4 for correcting the sampling and having an exact sampling at the end. So thanks to this method, we can uniformly select a number of subqueries. For instance, in this example, we draw 4 queries. One for Julia the Elder, one for Julia the Young, and one for Marcus and one for Leonardo. And we obtain an approximate answer by summing all these results. And we can observe that for gender and cardinality of 1, we obtain 66% instead of 64%. So we have a good approximation. An interesting point is that this approach is easily parallelizable, and it does not require a lot of memory storage. So it's a very good approach. And we proved that this approach converged towards the exact solution. So now I will illustrate this approach on 2 use cases. The first one is just the computation of most prominent properties and classes of linked open data. We use 100 public Sparkle endpoints available at the moment of the experiment. It consists in around 50 billion of triples. For the ground truth, we use the convergency of the algorithm. So we plot the accuracy of the prediction of the most prominent classes and properties according to the time. We observe that after 100 hours, we are around 90% of accuracy with a very small portion of the linked open data. This is what is interesting. We do not have to download a lot of information. In a second use case, we estimate the representativeness of linked open data. This is based on a work that we presented last year. The idea is to estimate if the linked open data is approximatively representative of the real world. So this is a very ambitious task. So we use the Benford's law, and we compute the first significant digit distribution of a property. And if this distribution is far from Benford's law, it means that there are a lot of missing triples. In this picture, in orange, there are 100 missing triples, for instance. And we are sure that they are missing in the real world. So we apply this approach. It concerns around 25% of the linked open data cloud, because we cannot apply this approach for all properties, unfortunately. And for these properties, we computed that the representativeness is only 50%, which is very low. It means that there are more than 13 billion triples that are missing, at least for this part of the linked open data cloud. So in this work, we propose a new approach for computing analytical queries. The main idea is to use an anytime approach. It is interesting because we can have a result at any moment, but we ensure that the final computation will give the right answer, and this algorithm is really efficient in practice. And in future work, we would like, there are plenty of directions, we would like to add reasoning capabilities, because currently we consider 2 equivalent properties separately. So, for instance, it's not correct. And in the future, we would also like to test other advanced analytical queries. So if you have some idea, they are welcome. Thank you very much for your attention.
in your work, you are assuming that the data set will not change, right? So the number of properties at the first hour will be exactly the same of the number of properties after 3 days and something. Do you have any idea what would happen if the data start to be more dynamic?
This is a good question. It depends, of course, of the evolution, if the rate, the dynamics of the change. But we could envisage to consider to deal with this problem by dumping previous results for refreshing the data continuously. But for the moment, this is not implemented. So we imagine that we have exactly the same data during the execution. And of course, in certain cases, we know that it is not right. So we just make an approximation.
Other questions?
Thanks for the presentation. You said that partitioning by the subject is actually complying with the fair use policies. How can you make sure that? I mean, how can you actually claim that? like
Your question is why the partition by subject is correct?
Yeah, the last one. How do you say that actually it is compliant with fair use policies?
This is a valid partition because if I consider the query, if I group, I add a restriction for selecting here the subject, we can observe that the aggregate here is correct for this subject. If I add a restriction.
I have no question about the validity. I have a question about fair use policy. Like, how do you know it is actually fair use?
Okay. Yes. The fair use policies, for instance, how we are sure that the time is sufficiently small to be accepted. Yeah. So we are not sure, of course. We have never any guarantee that the triple store is available. Yesterday there was a presentation about Sparkle endpoints, and most of queries doesn't work at all on public Sparkle endpoints. So we are never sure that it works. But we select the smaller query, the smallest query which is possible and which is valid. So this is likely to be probably the best candidate for be compliant with fair use policies.
Okay, thank you.
But it really depends if the data is indexed or not, right? Because if you are querying on the run and the indices are missing, is just taking way more time than you may expect. The way they archive the data, it's really important for you because your assumption that extracting less data will be faster works only if there are proper indices on the variables that you are going to access.
Yes, we have an assumption about that we can ask certain queries to the triple stores. Otherwise, we cannot calculate anything.
Okay. Okay. Thank you again.
Can everyone hear me like this? No? I'll take the mic then. Take this.
Okay, the next talk is from the journal track, and it's titled Triple Storage for Random Access Version Querying of Rdf Archives, and the presenter is Ruben Teilman.
Thank you. So my work positions itself within the domain of Rdf versioning, where we assume that different versions of a certain data set can exist in parallel. Like, for example, we have different DBpedia versions, and in some cases it makes sense to query different versions of DBpedia, and sometimes even query over different versions to, for example, calculate the differences between them. So the main focus of this work was how to enable these multiple versions to be stored in an efficient way while still enabling efficient version querying across them. So this presentation will be split up into three main parts. So first I will be introducing a bit the fundamentals around Rdf versioning. Then I will introduce our storage approach, and finally I will show you some of the experimental results on top of our approach. So first, the fundamentals. So in Rdf versioning, we basically see an Rdf version as a set of triples annotated with a certain version label. Like this label can be a string or an integer, can be anything. So on top of these Rdf versions, we typically consider three main types of so-called query atoms, so ways you can query over these versions. So the first one is called version materialization. This is the simplest one, where you basically select a single version and do any kind of query within that version, like, for example, which cities have existed in DBpedia version 2016. Next, we have delta materialization, which queries the differences between two given versions. For example, which cities were created or removed between 2015 and 16. And finally, we have the version query. That's a bit of a special type, where we query all the versions at the same time, but we annotate the results with the versions in which the results are actually valid. For example, in which years has Brussels existed across all DBpedia versions. So in order to support these different kinds of query atoms, several so-called storage strategies have been proposed. The first one is called independent copies, where we essentially store every version separately in a fully materialized store. The advantage of that is that this is very fast for version materialization, but slower for the other query atoms. And another downside is that this typically consumes a lot of storage space. Next, we have the change-based storage strategy, which only stores the differences between each consecutive version. This is then fast for delta materialization, but slower for the other query atoms. And the advantage of change-based compared to the previous type is that this typically consumes less storage space. And finally, we have the timestamp-based store, which essentially stores everything in one big store, but the triples are annotated with the versions in which they actually exist. This is fast for version queries, but then slower for the other types. And also requires a bit less storage space compared to independent copies. So as you can see, each storage strategy has their advantages and disadvantages, so there is no one single optimal solution if you want to support all of the different query types efficiently. So yeah, our goal was to come up with a hybrid storage strategy which combines the advantages of all these different storage approaches. So hybrid storage has been done before already. Typically, what we see is that the independent copies and the change-based approach is combined, where we start from an initial snapshot, so fully materialized, and then we store each version as a delta compared to the previous version. Now, this approach has some disadvantages. The main one is that this does not scale that well for very many versions. Like, for example, if you want to query version 5, you basically have to apply this delta on version 4, 3, 2, and 1, and 0 before you can do any queries on top of this. So if you have really large amounts of versions, this does not scale that well for version materialization. So our solution for this is to modify this chain of deltas a bit, so that instead of making the deltas relative to the previous version, we make them relative to the initial snapshot. So in that case, independent of what version you want to query, you only have to apply it to one other version, basically. So in that sense, it scales a bit better. But now we have another disadvantage, which is that actually the changes across these different deltas will accumulate. So the deltas will start becoming bigger. So to solve this, we actually combined this with the timestamp-based approach, where we essentially, my slide is too small, let me zoom out. No, never mind. So what we essentially do here is we combine, or we store all of these deltas in one single store. So we follow the timestamp-based approach, and we annotate each triple or addition or deletion, essentially, with the delta version in which they exist. So in that sense, we have actually combined the independent copies approach, the delta-based approach, and the timestamp-based approach. So that's, in general, our storage approach. So on top of this, we support, or we introduce some querying algorithms for the 3 different query atoms that I discussed before. So in this case, we focus on pure triple pattern queries, as these are the foundational building blocks for more complex Sparkle queries. We also support streaming results to enable a more memory-efficient processing of results. Another interesting aspect is that our algorithms support efficient offsets, and this leads to more efficient subsets of the results to enable use cases like pagination. I won't explain these algorithms in detail here, but they can be found in the paper. So that was our approach. Let's have a look at some of the experiments. So we implemented our approach as a system called Ostrich, which stands for Offset-Enabled Triple Store for Offset-Enabled Store for Triple Change Sets. We implemented this in C and C++, and it's open source, available here on GitHub. 2 important things about this: we made use of HDT for storing the initial snapshots, and we use Kyoto Cabinet for storing the deltas. So Kyoto Cabinet is essentially a very efficient B-tree implementation which allows memory mapping. So in order to do our experiments, we made use of the Bear benchmark, which provides 3 real-world data sets from different kinds of domains. And they provide triple pattern queries for the different query atoms that were discussed before. Another advantage of Bear is that they offer baseline implementations for the different kinds of storage strategies using HDT and Jena. So we did several experiments, but they can be categorized into these 2. So first we did some storage-related experiments to measure storage sizes and ingestion times. And we also did some experiments to measure query execution times for the different query atoms based on triple patterns. I will just show you some of the main results. More results can be found in the paper. So the first result we saw is that So storage size and ingestion time scale linearly. So in this case, we have a data set, so the bare A data set, which contains 10 versions, but each version is quite big. Now, if we look at another type of data set, so the bare B data set, where we have a much larger amount of versions, but each version is much smaller, we still kind of see a linear evolution, but here in the ingestion times, we see something weird going on around version 1100. So what you actually can observe here is a first limitation of our approach, where we see that the deltas actually start becoming too large, and they don't fit into the main memory of our system anymore, which causes the system to start swapping to disk, and this is quite expensive, so that's why you see this slow down. Now let's have a look at some of the query execution times. So on this figure here, you can see the average lookup times for different systems for version materialization, so across all of the different versions. So what you see here is that, so for ostrich, so the red line, you see that execution times remain constant and dependent of the version. And ostrich outperforms all the other approaches except for HDT IC. So if you remember from the start of the slide, so the IC stands for the independent copies approach, which essentially stores every version as a separate store. So in that case, it makes sense that this is faster than the more complex storage approach, which is at the cost of more storage space. Next, here you can see the same figure, but for the delta materialization queries. Here you can see that ostrich actually outperforms all of the other approaches, except for the HDT CB approach, so the change-based approach, for the first 100 versions. But after that, the CB approach starts becoming much slower. And finally, we have the results for version queries, where you also see that ostrich outperforms the other approaches. So those were the main results. So in conclusion, we introduced a hybrid storage strategy, which combines some of the advantages of the different types of storage strategies, and this enables query execution times for the different triple pattern queries, with execution times being around 1 millisecond or less. These query algorithms are offset enabled, which enables things like pagination, and we offer an open source implementation in C and C++, but also JavaScript bindings exist for simpler implementations in JavaScript. Thank you.
Thank you for your presentation. It's a really interesting approach. I just wonder if we would like to implement it using Git. Can you reuse some Git functionality, for instance, for storing deltas or for combining this snapshot plus several deltas?
So your question is if this system could also be implemented using Git, right? So that would be like the green part here, right? Yes, I think that would be feasible to use Git for that, but I'm not sure if Git would be efficient enough to handle like really large versions. At the moment, the way we do this is we use, where is my slide? So we use the system called Kyoto Cabinet, which is a very efficient B+ tree implementation, which allows deltas or just in general things to be stored that are larger than will fit into your main memory. I don't think Git, but I'm not sure about it, but I don't think Git supports deltas that are like huge. So that's the main reason why we use Kyoto Chemnit for that.
Hi. So, Ruben, I was checking your NPM entry. Would you mind elaborating a little bit what's included in the package? Because it sounds like you include the triple store and the bindings, right? Is it a full server-side solution?
Sorry, what NPM package?
So I'm checking the node package management system for Ostrich, and it sounds like you have both the versioning and the triple store in the same package. Is that accurate?
So the triple store. So what Ostrich is, it's a full implementation of like the full storage approach and the query algorithm. So everything is contained in there.
Thank you.
And the node bindings are just simple bindings to link to the C++ codes.
Does the delta or the difference between versions affects your approach or the others? The difference, if there is too much, there is a lot of difference between each version or very little difference between the successive versions, does that affect your approach or the others, in a way? And maybe related to that, you generated a number of versions, right, to test your approach. What was the delta between them in your experimentation? Yeah,
well, good question. I'm not sure if I have a good answer for it. So we made use of this Bear benchmark, and they offer different types of data sets. So like the Bear A benchmark is, for example, a data set with just a few versions, but each version is very large. Then the next data set, so Bear B, is one where they have many versions, but each version is very small. But I don't really think they make a big distinction in like having varying delta sizes. Not sure if that's the case. I think the delta sizes for each version is about the same, I think, but I'm not sure about that. I would have to look into that.
Hi, thank you for the talk. A bit similar question. Do you think there is an upper limit in how many snapshots you can actually save? Because you put them all together. Like at some point, probably the snapshots in total, the deltas in total will be bigger than the snapshot itself. Any intuition on this?
Yeah, that's a good question, actually. So in this figure right here, you can actually see that our system already starts reaching its limits. Well, I'm not sure if this is a limitation of the approach, but at least of the implementation or the system it runs on. But one of the things we plan to look into is when the number of versions starts becoming very large, like for example around version 1000, we could say we stop the delta chain here and we create a new snapshot, and then in that way we can start from scratch again, basically. So
good. I have a quick question. The way you are storing the data, that is, you are always referring the data to the first snapshot, suggests that you can parallelize a lot the query execution, because you can work on each base version plus snapshot in parallel and then post-process the result to combine them. Have you ever considered this?
Yeah, actually, like, it's not part of the system we evaluated, but we did some experiments for that. But yeah, we did not carry on with that because the implementation in C++ for doing parallel things was quite complex, so we ran into many issues with that. But I think it would definitely be interesting to continue investigating that because indeed there is a lot of, well, at least two parallel things that could be done there. So it would be a useful thing to look into, yes.
Okay, thank you again, Ruben. Last talk of this year conference, Niklas Kolbe from the University of Luxembourg will explain popularity-driven ontology ranking using qualitative features.
Can you hear me? Yeah. Okay, hello everyone, and thank you for attending this session. I would like to present you our study on ontology ranking. So I will start by introducing the problem that we looked at and why we were motivated to perform this study. So first of all, what is ontology ranking? So ontology ranking basically comprises a user query, which is expressed in terms of keywords. So behind the scene there is an ontology repository, so a set of repositories that we are looking at. And we have a set of relevance and importance features which decide then how do we rank these ontologies to answer the user query. So what we see on the right is just an example. It's the well-known linked open vocabularies platform. And it offers exactly that. So people can type in their search and they get the ranking about what is most relevant. So relevance features basically mean how well does the query match the ontology, and importance features are qualitative criteria about the ontology. So we were motivated to perform our study based on the Web of Things case. So we see a lot of research projects where there are a lot of people from different backgrounds which want to use semantic web technologies in their projects, and they don't necessarily have the background or the domain knowledge to know which ontology to reuse. And we see also a lot of scientific output in terms of studies which review these ontologies and domain ontologies, which makes it really difficult to get the overview. So this is one aspect to it. The second aspect to it is that in the semantic web there's this notion of popularity, which means there's an incentive to reuse an ontology if it has been reused before, because the idea is we should not kind of reproduce a new ontology or produce a new ontology if it's already out there. And it's very important that this is reflected in the ranking because it gives kind of this community consensus of what actually is relevant. And the state-of-the-art tools do exactly that. So the linked open vocabularies platform has a feature which measures the popularity of an ontology. And for this, they use the number of occurrences in the linked open data cloud. So yeah, there is some data set, and they see how often it had been used. And it's a very nice tool. We looked at this, and we looked at the metadata, and we looked at how much information about this popularity is actually out there. And we identified that there are several domains where there's actually no feedback about popularity of ontologies where this measure comes from. So we found services, industry, IoT, transport, health, and security where there's actually no ontology that is contained in LOV which has any usages. And I mean, I'm sure that people in here know a lot of these ontologies, of these domains, and they would be able to make this distinction. And we think this is a problem because people have a lot of trust in this kind of search. So they will probably make a query and they will look at the first 3-4 elements and just pick one. And they think that this ranking reflects this kind of relevance. But for these ontologies, it obviously does not incorporate any score because there is no information available in that sense. So, this is our problem. This motivated us, and what we then want to look at. So, what we did in our approach, we wanted to look at: can we refrain from using this explicit popularity score, and can we predict it, the relevance degree, by just looking at the quality of the ontology? So, to be independent from how this popularity score was computed and maybe how the data set was the data sets were assembled. And we do this by learning a ranking model which uses as a target the popularity, or for the relevance degree, the popularity score. So this is basically our hypothesis is, can we predict this relevance degree by relying on qualitative attributes, and then we would be independent from this missing information about popularity and maybe give a fairer score to ontologies which are new, or where we simply can't get this feedback. So this learning to rank problem, I think the main challenge is to build this data set. So I will talk a bit how we built this data set in order to perform our experiments. So the first aspect is what are we actually considering as criteria for ranking. So we first consider like a very compound relevance match, because we really want to find, okay, first of all, we want to find the elements that are relevant to our query. So we use a standard search, we make some query expansions with Word2Vec and WordNet. I'm not going to detail how we extracted these features exactly, but they are reported in the paper. And then we also add several importance or quality attributes, which we then use to predict this popularity. So these are fairly simple features or characteristics that we extract from the ontologies. And in that sense, we don't propose any new criteria. So we selected these quality attributes based on existing surveys and other literature reviews, which where these criteria were proposed. So the second thing we need is ontology collection. So there is another open project which is called LOV for IoT. It basically tries to give a second life, so to say, to ontologies that have been proposed in the literature. And it's also a nice open platform, so we use this to collect some ontologies. We managed to download 455 of them, and 433 were then indeed syntactically usable. And this platform not only lists these ontologies, but it further comes also with metadata about it. So they describe the domain the ontology belongs to. They describe which sensor devices are described in this ontology. And they also provide the information in which publication this ontology has been published. So at the end, we end up with a triple store with 1 million triples and 133 different terms. And interestingly, this project aims to add these ontologies to LOV. So we see that a lot of new ontologies are added, but then again, the ranking doesn't really reflect their popularity. So the most difficult part is how do we get the labels, because the learning to rank is a supervised machine learning problem, and I just said we can't get this feedback about popularity from the linked open data cloud. So what we used the feedback about the publications. So basically the publication of the ontology, which we took from the Love for IoT catalog. So we crawl the citation history of the publication, and then we take two measures into account. One is how often it has been cited per year, that's an absolute value, and then second, we consider the linear trend of the citation history to see maybe the citation trend goes down, so maybe it has been replaced by a new version, and this should be penalized or should be recognized. And with this approach, we overcome several limitations. So we don't need to rely on this linked open data sets, first of all. At this time, we didn't have any access, for example, to user click logs, which is also often used as relevance feedback, as implicit relevance feedback. We could also have made a human study, but it also has negative sides. So human studies can also be biased. They're very costly, like a lot of effort is involved. And this approach that we chose is automatic, so we can reproduce it and we can update our data set over time. So for each ontology we get a popularity score through that. And as it's common for learning to rank, we map this to a relevance label from 0 to 4. And this basically forms our data set. I put one example here. So there's, what I didn't mention. So to generate the queries, we use the domain and sensor device annotation. So for example, there are ontologies in the catalog which are annotated with a sensor. So we use that at query, and we consider all the ontologies which have this tag as relevant. And the relevance degree is then derived from the popularity. So a high popularity score ends up in a high relevance label, like 4. And then we extract all the features that I mentioned, so different feature scores. And we also add we randomly sample some negative examples so that for the learning algorithms to be able to distinct that. Okay, so then we performed some experiments. Basically, we performed 2 experiments, but I will focus more on the first one. So what we see in the left box is basically what I just described, how we created that data set. So we took the log for IoT and scholarly information, we built this ground truth and make the feature extraction, and now we use this as a training set for learning to rank. So we use a algorithm called lambda mart, and we use tenfold cross-validation, and have a ranking model in the end, which we can evaluate with standard information retrieval measures. We further derived 2 other data sets. I will not go into detail, but essentially what we want to do in the second experiment is to compare our ranking to existing rankings, like the one from LOV, and we also compare it to BioPortal to see if the ranking model which we just trained is actually doing something reasonable compared to existing rankings. And I should note that LOV and BioPortal both take this popularity feature into account for their ranking. So, what I forgot to mention is that we do this for 2 configurations. So in the first configuration, we only consider the relevance features without taking into account the quality criteria. And in the second configuration, we consider all of the features. So we are mostly interested in the normalized discounted cumulative gain, which is in the middle, and the expected reciprocal rank, because these evaluation metrics take into account the relevance degree. And we are also mostly interested in the comparison of these two ranking models. So we show the different average performance with the red line with these 2 models. And we can see that if we take the quality criteria into account, we are able to better predict the relevance degree in popularity measure, in terms of popularity. So we conclude from this that, yes, if we take quality criteria into account, we can predict the popularity relevance. In the second experiment, we used the model that we learned in this experiment and applied it on the test sets that we derived from the other existing APIs. And the blue line that we see here is just the performance that we had on our first test set. And on the first row you see the results for LOV, and on the second row you see the results for BioPortal. And we have the same observations. So as soon as we consider the full model together with the quality criteria, we see an increase in the information retrieval performance. So when we learn a model, it's also interesting to understand what it's actually doing, which is quite difficult with lambda mart. It learns a set of regression trees. But what we can look at is we can look at how often a feature is used for the classification. So it gives us at least an impression how important a feature could be. So what we see is that, of course, the relevance features are very important because they decide whether the query matches the ontology or not. But we can see also distinctions in the quality criteria, how often they have been used for classifications. So, for example, we see features like PageRank, which basically defines how often, gives a score based on how often the ontology has linked by others and what their important value is. Understandability is, for example, a feature which measures how many terms have labels and comments and so on. So these are important criteria which make sense, because if these things are there, then it's more likely that it has been reused or that it will be reused. On the other hand, the criteria which we call believability, it's related to whether there is author or other provenance information, has not really been used by the model, which was surprising for us. So when it comes to the limitation of our experiments, so we make the assumption that the scholarly information about the publication of ontology actually gives us the feedback about the ontology's popularity. So one may question that because we don't actually know the reason why publication has been cited. But again, we use this approach to overcome several limitations of other approaches, and it also comes with some advantages. So, we made this assumption for the study and based our things on this. But the idea that to use this is not limited to IoT or limited to how we derive the popularity measure. So there is room to replicate this study for other cases. And also from ontology reuse perspective, we simply consider covered the easiest case where we have a query and we provide a list of ontologies, but often engineers are more interested in seeing ranking the terms of an ontology or ranking combinations. So in that case, we have only a very simple problem setting. So to conclude, we show that we can predict the ontology's relevance in terms of popularity with qualitative features, and this makes the ranking model independent from this explicit popularity metric. And in the end, we have now a ranking model which can be applied on ontology collections with Web of Things ontologies. And also we discussed the importance of different qualitative features in the paper on the overall performance on the ranking model. And we make our resources available, so if anyone is interested in looking at the dataset or building their own model or use the model that we learned, he's free to have a look. And just to conclude, we also have a prototype in development just to play a bit with the ranking and get an intuition how well it is working. And we plan to expand the study with more features or apply it on different domains and finally deploy this interface somewhere so that it can be used to find ontologies. That's it.
Thank you.
Thank you for your talk. I have a question regarding the qualitative features you mentioned, because often if I want to reuse an ontology, the relevance to me sometimes means like what is relevant to my specific use case. For example, if I have a use case where I need a lot of machine understandability, that I want to have certain axioms to be present in the ontology, yes or no, for example. So my question there would be, do you think it could be integrated in addition to the actual query, like some sort of a filter where I could say, I want to have only ontologies which use, for example, disjoint class statements or something like this. Would that be feasible, and could that be included in the relevancy measure?
So I would say yes, the short answer. The long answer is I think what you're talking is about like personalization of the search, right? Or changing the query. I mean, we consider really the simplest form where you just have the keyword query, but in essence you can also think of cases where you have extra filtering options. I think this is what you're referring to, or other search criteria. This is actually no problem to take into account. All that changes is the query ID. So just the person might have the same keyword query, but if you have different filters, it becomes essentially a different query. So but it's not a problem to consider this in the learning Turing session.
Hello. Sort of a follow-on from that. So your ground truthing information comes from scholarly citations, but in industry and in utilization environments like government, a better metric for what is acceptable or popular would be maybe instance data. So how difficult would it be to inform the popularity by looking at instance triples out there? So say you've got very large collections of triples, you could say what is the use, therefore the popularity of the ontologies there, and use that as a similarity metric. Would that be easier than using citations, less mining?
So I think you're referring to RDF datasets, like in the linked open data cloud, for example, right? Or yeah. I mean, yes. I mean, actually, in my initial motivating scenario, I was talking about datasets. So this is basically the state of the art. They look at the data and see how often an ontology has been used to describe the data. Maybe I was not precise enough, but again, I think this is a very good feedback for any use case where you intend to publish your data eventually in the linked open data cloud. But what we were looking at were use cases where you, for example, in the IoT, you have data streams, and this data simply doesn't end up in these kind of data sets. So you actually don't have this popularity measure in these kind of scenarios. But I mean, this measure of popularity eventually is also somehow a philosophical question, because people might have different opinion about what popularity means. And you also mentioned industry. I mean, this is some of the points. It's really, really hard to get any feedback from the industry. I mean, you don't know what they use behind the hood, and you don't know what their views on that topic.
Hi, my name is Romana Pernišová from the University of Zurich, and I have a quick question also actually about the popularity based on citations. And I was wondering, did you maybe find cases where there were multiple citations for a paper, not citations, sorry, multiple papers for an ontology. So the ontology evolved, and did you, how to say this, did you sure that you include all of them, or is that not possible yet?
So I think this is one of our limitations of our approach. So it's a good question. I mean, essentially, you'll often have the case that people write more than one paper of their ontology. So in that sense, I mean, we basically just work with one publication in this case. But yeah, it would be much better to actually see if the ontology changes and see the evolutions or the different papers about it. Yeah.
I have a last question. Oh, any other question? Okay. I have a last question. I was wondering, when you studied the variable importance, why you went looking into the frequency and you just didn't use some more state-of-the-art solution like variable selection or trying lasso regression or something like that to understand which variables are really important for your prediction?
I mean, well, I mean, mostly we were interested to see, well, we used frequency because maybe it was the easiest measure to get during the development process itself. So, I mean, when you tune your model, you can easily extract that information about how often a feature has been used. So maybe it's more a practical motivation why we chose to measure it like that. Does it answer your question?
Somehow we can take it later.
Okay.
So thank you for attending this session, and time is up. Now we have 18 minutes of break, and then we meet again in this room for the awards and closing ceremony. Enjoy your tea and coffee.